Oh, hello there. I guess what's going on? Memes here. We're back. I apologize. I got into a little fight with my computer. I'm like, why does it keep on adjusting my brightness and everything? So you do the Google thing. How do I stop this? And you do the thing. And then it doesn't work. But you're not here to hear about my technical difficulties. All right, let's jump right into it. And what we're going to be talking about today is, and we've talked a little bit about this before, the radius of the proton. Because protons, it's or whatever the thing that we attribute with the properties of the thing that we refer to as the proton. Um, we've known about it for 100 something years or so, and we have its mass to like 12 significant digits. We have its charge to like 12 significant digits, maybe 10. And maybe there's some error in some of those. But we got a lot of information. However, its actual radius, that as we like to describe it, which is technically its root mean charge square radius, which is probably the answer right there. We used to believe it was like 0.87 femtometers. That's like 10 to the minus 16, extraordinarily small. And then there were some more recent measurements, and some of those kind of seemed to get validated, and it went to like 0.84. Now, that's only like a 3% difference, but when you're talking about in the realm of particle physics and stuff like that, and that's supposed to be a constant of nature, it's like that's a pretty big difference. Like, what is it? If you adjust it like the fine structure constant by like, I don't know, 3 to 5% or something like that, it's everything as we know would kind of get wonky. Might be a little bit higher than that, but typically, yeah, it's a good thing it's right about 1 over 137-ish, or 137.035,999, and then we argue about the 10th significant digit. Okay. So let's bring up the tabs. All right, let me share with the class. So the reason I'm showing you this is because I can do a calculation. Okay, it gives me a number. Big whoop. It's like you can add in enough stuff and things and epicycles, if you would, to get just about whatever number you want. So one of the things that I at least attempt to do, because, well, I'm a gamer, is look for a way to computationally reduce what is going on. And what might be going on? Let's bring it up. Okay. So we've gone over this before. This is the interesting apparent relationship um, between things like the proton, the neutron, and the electron. And this is basically quantifying stuff and things by the elementary unit of action, Planck's reduced constant, aka hbar. And the whole reason I got into this, and people have done stuff like this before, and they've had calculations that seem to line up. I think, was it Nassim? Oh, I forget his name. I know Anastasia and Shiloh from the Demystify side. They had interviewed him before. I had the the thing I have is some folks. It's like if you're gonna say something out there, and don't get me wrong, science can seem really woo woo at times. It's like, oh my god, where's the cat? Is it dead, alive, awake, asleep? Who knows? Oh my god, there's spooky things that may or may not happen, or correlations at a distance. Long story short is when people start seeing things, and it might be the case, and then they start, I tend to drift away from because I am a crazy person. But long story short is I think he did also predict the proton mass or the proton's radius back in like 2012. I've seen other papers talking about this, and I'd first come across it from Dr. Alexander Unziker. He had mentioned that if you did, what was it, like pi divided by 2, you put in the proton mass, the speed of light, and then the proton radius, it comes out to be close to Planck's constant, which is h bar with a circle, or 2 pi. So yeah, you get like the first 2 or 3 significant digits. So yeah, it's pretty close to Planck's constant. So it's, well, but can we do better? So all I did was, well, let's do this. Lop off that and see what we got. Okay, well, we want the proton as units here. All right, speed of light, root mean square radius. Hold on, multiplication, because I'm comparing a bunch of random things, apparently. So it gives you this number here. Now, this number doesn't mean anything to me. It's like, what? 4.2 times 10 to the minus 34. Yeah, joule seconds. I don't know what that means. Okay. You're like, okay, well, it's about 4 Planck's constant. It's like, all right, well, let's do this. 4. Okay, it was kind of close. Wait, did I need to divide by 4? Maybe that's what it is. That was an error on my part. Okay. So it is really close. You divide by 4, and it's like, all right, well, we got about 1 point. That should be... Okay, so it's close. It's close. If it's rounding up, okay. Can we do better? We got like 2 significant digits. If we got these things to like 10 significant digits or so, we need to do a bit better. How can we do a bit better? All right. So let's just, for sake of argument, we got our proton mass. We got the speed of light. We got the proton radius. This gives us at least the dimensions of energy. Because you got a mass. Hold on. Radius. There we go. So we've got... Am I saying this right? Oh, no. Okay. It gives us the dimensions of action, which are joule seconds. I apologize, because a joule is energy, and when you multiply it by seconds, like we were talking about yesterday, you lose one of the time derivatives, or whatever the thing is, goes from time squared down to just action. So we've got a mass times a speed. We got mass, a length, and a time. That gives us momentum. And now we're adding in a second unit of length. So we go from mass, let's just do kilograms. Let's do meters, divide by seconds. Okay, I should recognize that. All right. So it's giving us joule seconds per meter. And then we add in another meter. I know. It's very, very noob. Meter. Oh, I'm making it very angry. Long story short is you get a mass, you get 2 lengths in there, or distances. You divide it by a second, and then you get joule seconds. All right, because I didn't type out the whole thing, so long story short is I look at this, I don't know what this means, but then you notice it's, wait a second, assuming proton root mean square charge radius for proton radius. Classical proton radius. What does this button do? Okay. So you go through here, you get 10 to the minus 37. That's worse. That's worse. I don't know what this means. Well, it's a good thing that Wolfram Alpha does the hard part for me. It's like, wait a second. This seems to be about 1 over 137th the reduced Planck's constant. That was the thing that made me go, I wonder. So, multiply by the fine structure constant, which is about 1 over 137. Here's the classical proton radius. Multiplication. And then to... No, I did... I should have divided. Oopsie. God. I'm so bad. I never would be able to do this stuff by myself. Okay. Root mean charge, classical, blah, blah, blah. I know. It's... And then to my shock, or perhaps not so much, it seems to be Planck's reduced constant. Why? If we take this, divided by h bar. Okay, so we get 1. But hey, trust but verify. What are we doing? H bar. Let's get all the digits. Okay, to be fair, when I'm going to do this, it's going to show more digits than there are. It's defined at 10 digits right now, so we need to stop at the second 7. Okay. So we go down to the 7. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we have the 10 defined digits as of our update. Okay, put that there. Let's look at the difference. This is what we got from our calculation. Okay. So I got 11.054.054, 571, 571, 828. Ah, means you're lying. Okay. So we deviated at the 9th significant digit because we only have like 9 significant digits for the speed of light, and it rounded that 17 up to a 2. I mean, that appears to be a relationship, I claim. Okay. So what is the point? Why am I showing you this stuff? Because I did this stuff before. Okay. Because there are interesting things that happen when you go through. So we'll go all the way back. Okay. Okay. Back. Did I go too far? I think I went too far. No. Okay. I obviously went too far. There we go. Okay. Oh, there we go. All right. The initial thing that I had on the screen that I then had to go through directly there. So I apologize on that. So let me, oh God, I haven't even said hi to anybody since I went live. Jeez, I'm so bad. But yes, welcome, David. I see you there. Welcome. Thank you for joining, my friends. Hey, Bill, good to see you. Good to see you. Okay. Let me see. Oh. That's too bad. Hopefully Kitty's doing better. Yeah. Yes. An awesome one's constant is tasty snacks. I mean, who isn't? It's literally what we run. Hey, man. I literally needed, one of the reasons I was late, I needed to eat another half of a meatball sub because that's kind of how we work. You kind of need that food and stuff to keep on going. Hey, welcome, Mark. Good to see you. And I am in Massachusetts through I'm leaving on Sunday, Thomas. I should be back around Thanksgiving. So if you guys want to catch up around them or early December, should be able to make that work. Okay. Friday I got to do a presentation. I'm sorry. I literally just finalized that stuff. I know I'm the worst, Thomas. I'm the worst. Okay. There's a whole bunch of stuff here. Don't worry about this. All right. So the reason I am showing you this is because I do this little calculation. And then I'm like, okay, so what of it? Okay. We're going to get into what of it. So what I did was, okay, I should probably actually reshare this for just one moment. Okay, so just to kind of go through here, we had that classical proton radius. What the heck is that? Let's just copy that. You put it in here. Basically, they're taking the mass charge equivalent. So basically, you're taking the mass of what we believe to be a particle-like thing. Okay. And some element that has these attributes. Again, particle might not be the best thing, but I think it's a useful idea. Okay. So it gives you this crazy number and everything. All right. What the heck is this stuff? So let's just copy that number, and then we're going to go back and literally we are making the assumption that all this jazz should be equal to h bar. Okay. The elementary unit of action, because well, when we put all this stuff in the classical radius, oh, we're getting the joule second. That seems to be the thing that helped, I don't know, issue in quantum mechanics and helped start quantizing things after good old Professor Einstein was like, These things appear to come in some form of quanta, whatever that might be. So long story short is we got all the same stuff. Rather than inputting that, we're just solving for x. Solving for x in meters to have it equal this thing. So you put it in there, Wolfram Alpha goes through all the math and jazz, blah, 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 blah. Okay, so it gives you this number. This is that number. Okay, let's compare it to our other number. Okay. 1.53, 1.53, 469, 469, 826, 18. It's the same number. Okay. AKA, this is the classical radius of the proton. Okay. So why again am I going over this at all? Okay. Because what happens if we adjust this slightly? Because this does seem to hold for other particles. So let's just do this real quick. So let's do electron. We're just swapping out the mass and radius. We're literally keeping electron. I swear I can spell sometimes. Electron. All right, we do all that jazz there. Okay, and it gives us the equivalent thing for hbar. I'm like, oh, this seems interesting. Well, the neutron. And again, I know these technically to our classification, these are not, except for the electron, is not elementary particles because there's other things. Now it wants me to do the speed of light. Because sometimes for some reason when I go to the neutron, I need to type out the full speed of light. Oh, come on. Ah, it doesn't want to work with me. Oh. I put these things in boxes. Okay, it doesn't want to compute. It doesn't like me anymore. Come on. Oh no! You've reached your query limit here. Neutron. Okay, now it's just being difficult. Radon? Neutron mass times the speed of light. Times that. Okay. Maybe. Okay, rather than belaboring the point, we can go back to that at some point. Okay. Let me remove this and we'll actually show what the why we're doing this stream about this thing and not another thing, because we had that there. God, it doesn't want to work. It hates me. All right, so we'll just do the Compton wavelength of the proton. That has a definition. It's literally just Planck's constant divided by the mass times the speed of light, because, well, that's literally what it is. So I show this thing right here. Okay. Okay. So Compton wavelength of the proton. Literally, you're taking full Planck's constant, so that hbar with a 2 pi. Dividing it by the speed of light times the mass of the proton. Gives you this value. This is a wavelength. So it gives you that distance. For some reason, Wolfram Alpha, it shows these comparisons, but if you actually click on it, it gives you a more appropriate one. That's basically the range of the strong force. I came to this via another thing. I was looking at the Higgs boson. It's like, oh, this seems to appear to be this, but it started to deviate. So I couldn't really justify it. It does seem to be around the same proportion. But so we can see here, this is the proton's Compton wavelength, 986, the last digits, 986, okay. So this is the Compton wavelength of the proton. Well, I also did type that in. So now the question is, we have this wavelength. I do remember Dr. Hunziker at one point saying, it's like, I can neither confirm nor deny. I may have sent him an email about this, and then at some point he did a video highlighting another paper that had noticed the same thing. They had it to, I think, like maybe 4 or 5 significant digits. I'm just like, I'm going to Wolfram Alpha, and it's about a decade or so later. We got more significant digits. Let's see what it would be. I think I cut off my search around like 7 significant digits, maybe. So you see this, and it's like, all right, well, at one point, I think Dr. Hunziker had said, well, it's well known that the proton's actual radius is like 4 times its Compton radius. I think he said something like that. I may be misattributing. If I am, I apologize. But when he was saying that, I'm like, well, if we've known this and we've had that calculation and we've known at least, I don't know, half a dozen digits of the proton mass for like 10 or 20 years, couldn't we have just computed it, and shouldn't we have like not been surprised? To be fair, this is 4 times the Compton radius. Yeah, that's not that 0.84 times 10 to the minus 16. Not quite. Not quite. So I'm like, huh. I just assumed it was true. And to be fair, this kind of confused me because I thought I was calculating the Compton wavelength from that original thing, and apparently I wasn't. Oops. So the question is, might there be an interesting ratio or something going on? Because in order to actually do this thingy, if we take doing it this way, see, I thought this was generating the Compton wavelength. It doesn't, because the Compton wavelength is that thingy, that 1.3 times 10 to the minus 15. Let's take the 4 out. So, I mean, that is close. That is close. And as you can see right here, it's about precisely 0.25, the proton root mean charge radii. Now, I mean, it's showing that, but to be fair, we have it to like 2 significant digits, I think. It's like 0.84-ish, and then we start to have the error. So I'm like, all right, well, let's just do that. We do that, and then this just gives us the value of 4 over alpha, so instead of like 1 over 137, we're getting 548. Okay, the reason why I may or may not have noticed this is, oh god, this is crazy. Let's, yeah, stop your computer from adjusting the gamma on it. Oh, that damn gamma. All right. What was I doing again? Oh god, I totally forgot what I was looking for. Oh, yeah, hbar C. Okay. Why do I say this? Partially because, again, I'm just the person that's kind of crazy that, oh, look, hbar C, aka the reduced Planck constant speed of light product, because you're just multiplying them together. That's 1. Okay. It happens to be precisely 548.143997b image potential energy constants. I'm not going to act like I know what the heck that is. I did the calculation before. Some energy. It's a version of quantizing energy. But long story short is 4 times the 4 divided by the fine structure constant gives you this ratio for h bar times the speed of light. That I just happen to be enough of a crazy person, and I'm like, wait a second. That difference, that 548 or whatever, I'm like, I think I know how to deal with that. And then again, Wolfram Alpha, at this point, it tells you it's 4. I didn't have it in this clean a formulation at first, but okay. So it's saying that it's equal to this, but again, measurement-wise, we only got like, I think maybe 4 significant digits, and there's like error in the last 2. Hold on. Go data, proton radius. You may or may not visit this page often. Okay, so right now, according to CoData, it's 8.4075 times 10 to the minus 16 meters. Okay, so ridiculously small, so like basically 0.84 femtometers. Okay. Those are usually what you have, but as you can see here, that's a decent size error. That means that could go down to almost, 8.4011, or it could go up to about 8.41 or so. Now, that at least appears, I claim. So 0.841. Okay, it seems to be within the standard error bars right there. I mean, that's kind of cool. And if it did have a relationship like this, I mean, very often you'll hear the term people say, we look for beauty, or sometimes I think was it The Rock or somebody, maybe Pauly, somebody is often credited with us saying that's like it's more important to have beauty than the, I'm like, I don't think they were throwing accuracy out the window. Now, you can have a measurement and you can add an epicycle after epicycle and have it exactly fit that measurement. If it exactly fits that just one measurement, maybe you should be wary, unless that is literally the highest precision we have, because one might expect there to be a little bit of error there. Okay. But this whole thing where it's like, well, this, we've got a thing that we can calculate from mass and everything. We got this that we end up relating all these different constants to. It just so happens to be elementary charge over the Planck charge squared, computationally reduced. And we just add an integer 4. Okay. And that gives us this number. Okay. So again, I have this calculated number, but we only got a couple of significant digits. What? We got like 5? Yeah, we got 5 significant digits and this significant error in the last 2. What do? Maybe we try to find another way to go back and forth. And maybe, just maybe, we can computationally reduce this whole jazz and maybe try to figure out what's going on. So let's do it. All right. Let's go back. Uh-oh. All right, Thomas. Well, at least as of now, I plan on being around for my birthday, which is also very close to your birthday. I think we're within about a week. Was it like the 24th or something? Oh, God. I have no idea if that's right. If that's right, God. I probably only remember that just because of the debauchery. I am not, again, this is why I introduce myself as a crazy person. Oh, no, you're pretending to be, no, I'm just consistently a crazy person. Bar, yes. What's the neoclassical radius? Oh, that might be a very interesting. Oh, where Neo bends the spoon. Well, I don't know if this is the way, David. This is just how I struggle through things. And again, there are probably folks that have this all figured out and stuff. It's just, again, you hear some of these things that people say, and then okay, especially on YouTube, and you're like, oh, these are smart people, and then eventually you go into something, it's like, that's not actually what Einstein said, and that's not exactly there, that was misattributed. That's why very often I'm like, listen, take it with a grain of salt. And again, full disclosure, I am not a PhD in mathematics nor physics. I am a crazy person on the internet that happens to be interested in these things, and just a monkey with a magic typewriter and maybe an idea of where to look. Well, yes, David, we're getting there. We're getting there. This is why algebra is awesome, because ultimately I look at this thing and I'm like, and often I stay up far too late and just like getting ready to go to bed, and all of a sudden it's like, oh, that's interesting. What's this? And my brain is tired. So then I'm trying to cancel these things out, and I'm like, all right, I got like a 4 over here. I got like a 2 pi over here. This should cancel out, but then I either make a multiplication or division error, frustrate myself, and eventually we get to something like, we had this guy over here. All right, so we're just taking our classical proton radius. We're defining it by alpha, the fine structure constant. That 1 over 137 number that nobody knows where it comes from, except maybe there are some ways to calculate that might not be mainstream, so to speak. Or, I don't like the word mainstream. I shouldn't be using that. Generally acknowledged. We'll say that. Okay. So, number one, my question is, well, maybe why is this 548 number appear to be here too? Maybe that's a connection. I haven't explored that connection. If somebody wants to explore it, by all means, please tell me what's going on. And again, this is in these dimensions. Bending stiffness, or I think they actually added in a couple more interpretations. Inverse, oh, sorry, I'm blocking it. Inverse distance potential coupling constant. I mean, that's what it is. It's because what's the distance potential coupling constant? If we notice the dimensions here, we've got mass in the numerator. I got a volume over here, and we're divided by time squared. If we look at something different, like, I don't know, big G, which we want the unit for the Newtonian gravitational constant. We got a mass in the denominator. We've got a volume in the numerator, and time. Literally, we moved mass downstairs. I think Anastasia did a tweet about this earlier, and she showed, like, okay, maybe we'll show that just because it's a playful thing, and I think it's useful to just. Stephen Wolfram has said that at least one of the things that maybe he learned from Dick Feynman, what Dick Feynman often used to do, he would like to break things into their individual constituents, into their simplest pieces, and try to figure out what's going on, and that's basically what Stephen Wolfram does, and that's how he ultimately came up with the rule he had, which maybe folks like it or don't like it, but I'm like, well, if you're going to postulate the entangled limit of all potential rules, I'm like, if you're going to go into everything that's possible, well, you could parameterize it by rules, and that's something he's apparently seems to have some talent at. What were we looking up again? Oh, Twitter. Sure. Where were we? Okay, so let's bring this up. So, and I'm just nothing against Anastasia at all. It's her and Shiloh put me and Casey and Minnie, his dog, up for the night. So, and they fed us and everything. So those are obviously the important things. Oh, I didn't retweet it. Huh? I'm obviously a terrible person. I retweeted the woo-woo stuff. Here we go. All right, let's share with the class now. Okay. Oh, I'm not gonna lie, David. I literally just read what you said there. I thought you were talking about something else. David is commenting. You put your first term in. You cancel like terms out. You put your last term in, and you make it all work out. You do the calculation, then you turn yourself inside out. That's what it's all about. I think you just summed my life up in a nutshell. Well played, sir. All right. Salty protons. Thank you. It's, I'm here for the next 27 minutes at least. Hopefully. All right. So, as we can see, Anastasia commenting here. Come on, guys. What are we doing here? Big G is approximately equal 6.67428 times 10 to the minus 11 meters cubed, kilograms to the negative 1, seconds to the minus 2. This is meant, so just a normal person looks at this and like, I don't know what this means. So, being the internet wise guy I am, I'm just like, I've embedded all those other comments. I apologize. We're just moving mass downstairs. Because, well, meters cubed, divided by seconds, mass, or kilograms, is in the denominator. You got a volume divided by time squared, mass is in the numerator. I mean, that's interesting. Why is it that hbar times the speed of light in the Newtonian gravitational constant is simply a matter of where mass goes? How very interesting. But I digress. Okay. All right, that was a little tangent. It's Yeah, no, that actually really was a good job. It just flowed. I'm just like, I, I just I just saw canceling out terms. I'm like, okay, so he read my mind already. But that was excellent. I like that. I think I'm gonna use that. I might just make a short. Oh boy. Okay. So we got all this crazy jazz here, and it's like, all right. So what might be going on? Um, I have this calculation, but again, I thought I was computing the Compton radius. I wasn't. So I'm like, well, if the Compton radius is something that we have to like, I don't know, like a bunch of digits, this is probably like 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we got this to 9 significant digits, but the proton, we only have 5. Realistically, about 3-ish, and because there's some error there, so ultimately 2 or 3-ish. Okay. So we got about 2 or 3 significant digits there. What the heck is going on? Okay. Oh, I'm not even sharing. I apologize. I'm waving and showing you here. Yeah, we got like realistically about 2 or 3 significant digits. Okay. So Compton, we got 9 significant digits. I'm like, all right, well, let's take the things that we believe we know within our coherent-based system that we have high confidence in. Maybe we could find a potential relationship. Okay. So it's, well, what happens if we take this and divide it by the other thing? This is why, like, I don't know, like maybe like 1 o'clock in the morning last night, I sent this tweet out. Where was it? This guy? Nope. Nope. This guy. Here we go. All right. So, first off, let's take a look at our friends. So our friends here are, oh God, I need to, again, trust, but verify. Actually, heck, don't even trust me. Just verify. All right. It's 1.3 yada yada times 10 to the minus 15 meters. Okay. This is that wavelength. Okay, let's actually just go through it. I don't need to share the dang thing. So let's just do Compton wavelength for the proton. And then, oops, I skipped ahead. Don't look. Don't look. It's gonna ruin the surprise. Okay, so let's just take this, like this length right here. That's the Compton wavelength is technically larger. We're just gonna divide these stuff into that. What do we get? Get this number here. I don't know what that is. Now, if I've scheduled a stream around it, there's probably something interesting if you couldn't tell. What is this number? I'm looking for something complicated and just try to delete digits and try to justify what I'm gonna match by. Okay. I was thinking about doing that, and then I'm like, wait a second. Now, there is some rounding going on there, but these things are the same. I think it's nixing. What is it? 1, 2, 3. I think it's nixing some of those digits there. Just go back for a second. Because maybe I'm just wrong. Okay, here's the thing I had from last night. It was more impactful when I actually put in all the digits, because I think Wolfram Alpha is rounding there, so that is something to be quite aware of. So long story short is when I did it last night, so I think I included maybe an extra digit or something there. Let me see. Did I? Oh, it's 9, 8. Okay, skipping 5. I did. Why is it right? Why is it? That's weird. Okay. But long story short is I'm like, all right, I do this. It gives this. And I'm like, pi over 2. The difference between the Compton wavelength of a proton and its radius it's a difference of pi divided by 2. Isn't that what Unziker said? Well, he was relating it in a different way. Technically, you divide by pi and 2, and in this formula, it's actually 2 divided by pi. But if you want to go from the proton's radius here to that, it's literally pi divided by 2. That's interesting. I claim, at least. Okay, so let's go back and actually do it, because obviously I'm a little confused. Well, actually a lot of confused, but we're slowly trying to figure out what might be going on. Yeah, Bill, Occam's razor. It's like, I'm looking for like some square root of all this. It's like, oh, 180 degrees divided by 2. That sounds like 90 degrees to me. Or at least in our numerical scale, so let's just take this whole thing. Okay. So it did round a little bit, so let's just do this. Let's just take the full Compton wavelength as it is. Okay, this is weird. Why does it have it? There's a difference there. I don't know. Maybe it's just rounding. Because some of these things you have to be wary. Some of these have like the actual data there, and then things like hbar, it's literally just Planck's constant divided by 2 pi. So it is putting, you could say it's hallucinating. This is something that Casey has stressed that I am noticing as I'm getting more and more precise with things. So thank you. Okay, so we've got this wavelength. Let's try pi divided by 2, because this is the Compton wavelength. Okay. That wasn't the right direction. Divide it. There we go. Okay. And then we get our number there. Because at 8.41, let's just click on that here. 8.41, let's grab another number that we had calculated. Okay. So basically, we went from the proton classical radius and dividing by alpha, the fine structure constant. And for some reason, there's a factor of 4 in there. I'm just doing the simplest thing that fits for maximum precision. We may have a reason for that. I have an idea. I need help, though. So basically, we get, our proton root mean square charge radius. So that's our calculated value via this whole crazy classical proton radius thing that some folks, they just like to ignore, but Wolfram Alpha happens to have it listed. Thank you, Team Wolfram. Okay. So this is our Compton radius. So we're taking literally the Compton radius of the proton. Okay. All right, excuse me. It's Compton wavelength. I apologize. I've been saying that. It's the wavelength. We want to be precise. All right, so it's this number here. We go through that. We then divide it. Pi divided by 2. We get this number. Let's click this number, and let's paste the other number we had. Okay. Maybe it's the same number. I mean, you can see it's literally 1. Or it's at least 1 according to this calculation to 1, 2, 3, 4, 5, 6, 7, 8 significant digits. Because if we're calculating its Compton wavelength via the speed of light, that only goes to 9 digits. And then if you want to, it could keep going, but it's just going to make up a whole bunch of just random stuff, because it's going to treat it as zeros, and we don't know that. And then that could be confusing. Okay. So it appears that when we skip ahead, this is what we get. So this is the Compton wavelength if we're using the classical thing. So it's literally, rather than 4, it's 2 pi. Okay. So because as I suspected David was talking about, we had a 4 here, and well, over here we had pi divided by 2. So if you could put the pi times 4 pi, and then divide by 2 is 2 pi. Okay. It took me far longer than it should have to realize that. Oh, I'm such a noob. Okay, so long story short is 2 pi classical proton radius divided by the fine structure constant gives us this, which, again, it annoyingly doesn't say it right there, but when you click on it, or actually I clicked on it right here, so we can see, oh look, that's the range of the strong force, aka the proton's Compton wavelength. And now it's saying it's approximately there, but 1.3214, 1.3214, and I think it's, what do they have there? There's a 6 on the end, and over here it's a 5. Okay. Because that's 1, 2, 3, 4, 5, 6, 7, 8, 9. You're dividing something with a 9th digit. Okay. I think that's allowable. Okay. So what we're saying is, from the classical radius of the proton, which we literally compute from the mass, we are literally taking the mass, and then there's a conversion where you can literally, we quantize it as a ball of charge. Okay. Well, why? Because, well, a sphere is what? A sphere is maximal volume. A circle is minimum area per unit R or something like that, I think. Something like that. Oh, yeah. When you're, I'm reversing that. Okay, I'm not gonna. But basically, they quantify it as a charged sphere. This mass, what would its energy equivalent be? Okay. I mean, why would we ignore this? Or just, is this just something that's not well known, that somebody like, a complete mad lad like Stephen Wolfram's like, I was a particle physicist. I'm going to attempt to create software that it's going to allow for symbolic manipulation, and then beyond that, I'm going to create a free website with, like, the perhaps greatest collection of units, conversions, and stuff and things in the world. And it's going to actually work pretty dang well. Is it perfect? No. But, again, it's... And I'm sure, again, there are probably some other folks that have looked at this, but it's, at least from what I found, it's like, yeah, folks were doing this maybe like 7 years ago, and they see like 4 or 5 digits, but we didn't have it measured at this time, and now it's like, well, we could compute this for a lot more digits. And to be fair, if you're trying to find that pi over 2 thing, it's, you have to try pretty hard if you only got like, well, 2 or 3 significant digits of confidence. And again, this is probably just simply a fact that if you just take, let's go to the Compton radius, or Compton wavelength, okay. Number 1, you have h there. That's Planck's constant, or h bar times 2 pi. So there's already a 2 pi inherently there, so that's what I'm thinking. This is coming in there, that factor of 4. Let's speculate if we would. Okay, so you can reduce it to basically this. The Compton wavelength of proton times 2 divided by pi. And this is my claim for what the actual radius, or root mean charge square radius, of the proton should be. The fascinating thing about, okay, maybe that is there. How does that really affect us aside from higher precision? Folks like Bill might say, well, higher precision is incredibly important because it's a metrologist. I would agree. Higher precision will let us do more cool things. Now, what about potential changes to the way we think about things? Okay. So what happens? I actually haven't done this. The It's the neutron Compton wavelength. Divided by this. Oh. That's interesting. Let me go back, and I'm just curious. I'm assuming it's probably going to come out to be the same thing. Hold on. I need to change this. Neutron mass times the speed of light. Just put a neutron radius. Okay, it's assuming classical rate. Oh, that's right. Because it doesn't have the neutron radius. Oops, sorry. It's not Wolfram Alpha's fault because they literally don't have data on the neutron radius. Unless, do they have the classical one? I think this was the extra step that I needed to do, was to actually calculate it. And again, this is assuming that you would see a proportionate equivalent to yeah, it's data not available. Am I spelling neutron wrong the whole time? Okay. So here's what we needed to do. We need to solve for x meters, like we did for the proton, and we're saying this equal to h bar. Okay. So it's giving us this number, which this looks very much like what the protons was. So this was our proton calculate. Okay, we got the proton in there. Here's where things start getting wild. And again, maybe this shouldn't be surprising. Let's take a proton radius and divide it into the neutron, because neutron, it's a heavier thing. It should be bigger, right? Oh dear. Wait a second. It should be greater than 1. Because the neutron's very slightly heavier than the proton. WTF, mate. Let's just subtract it. Similar terms. Okay, so there's a slight deviation around the 21st decimal place. Oh no. What the heck does this mean? Okay, let's go through it. Let's simplify this down to something much neater. Okay. So this, okay, last digit 72. Last digit 72. So this is the neutron. Classical charge thing. All right. So let's do this. Let's take our same equation that we had up there. All right. So let's take that out. Let's plug this in. Or what did we do? We did, should be, oh, actually, let's just do all this. This is meters. Because that was the unit we were solving for x for. Divide by the fine structure constant, and then what did we have there? We had, okay, 4. Okay, let's literally do that. 4. This number does look familiar. You got it, huh. So look, the neutron's Compton wavelength, or 2 divided by pi, so 8.4. Hold on, let's move this guy right over here, so it's next to it. Oh god, hold on, I pulled it out. Help. Okay. So, all right, so just to verify, 8.4, 0, 0. 8.4, 0, 0. 7766. 7766. Okay, and then we run out of digits there, and then that's got a 2 over there. Okay. Times 10 to the minus 16 meters. Times 10 to the minus 16 meters. So the interesting thing here is, let's go back. Let's take a look at the proton Compton wavelength. Okay, so in femtometers, 0.8 8.8412. In femtometers, 8.40076. According to my calculations, or Wolfram Alpha's rather, it appears that the radius of the neutron is just a wee bit smaller than the proton. WTF, mate? Again, I've seen that, and again, to me, I'm just a fool. I've watched Dad literally do calculations that kind of suggested this same thing, where it's like, wait, does this suggest that the neutron is actually smaller, at least according to these calculations and parameterizations that we have within our system, than the proton? Seems weird. And again, the neutron has some some weird thing where it's okay, it's a little bit less than this, and okay, it's like how big is a neutron? So about 1.7. It's on the same order of magnitude is not a hard boundary. Okay, because there's different stuff and things going on. Okay, so mass. Oh, we get a bunch of digits for the mass. It's charge. This, all these different quantum parameters and everything. I don't see radius. Okay. So again, they have it at about, what, like one significant digit? Something like that. That should be about 10 to the minus 16 or 0.8 femto. Oh, because they're having it in 0.8. Okay. Oh, because femtometers is the 15th power, and then, okay, it's like only one magnitude. All right. So, and then neutrons decay and everything. Okay, so fantastic. Again, should we really be that surprised about this? Because there's apparently a phenomenon, and I remember hearing about this like a few years back, where it's like, the weird thing is, you add mass onto stuff, it gets bigger. Except if you throw mass into a neutron star, what happens? It gets smaller. Why? I'm just saying that if you're saying that the gravity is so great that it's crunching things down, but then when you hear about it more, it's like, well, a neutron star, it's just a big bunch of neutrons. And then you go into some of the more literature, it's like, well, there's still some protons and there's some other things in there, but it's mostly neutrons. And I'm like, if you're adding more mass, your effective gravitational force is going to increase. And it's smushing everything together. Like, aren't you just converting it into like a higher and higher percentage density of neutrons? And if neutrons are just a wee bit smaller than protons, then, I mean, is this why? And again, these are testable results and everything. Again, we only have so many digits. Could be completely wrong, but as Bill was saying earlier, I usually am just looking for Occam's razor. It's like, okay, maybe I could do all these different loop diagrams, do all this and that, this and that, this and that. And it's like, that's cool. There's plenty of people doing that. I'm a simple dude. I just want to be able to type in some magical words. Look at this, divide it by a circle, half a circle, a quarter circle or something, and be like, oh, what might this mean? If I find other folks out there that are working on similar things that maybe have discovered other interesting things, it's like, maybe I'll reach out to them. Maybe they'll reach out to me. Maybe we could have some form of collaboration to better figure out what's going on. Now, at the same time, it's like, you'll have some folks and they'll do the whole poo-poo and all of academia. It's like, yeah, I have no idea. I had a fairly decent experience within academia personally. I I learned a bunch of things. Was it necessarily necessary for what I was looking to do? Probably not, but it was an experience. Um, but I'm just I'm looking for things, and now that we're at the hour mark, to come full circle, I'm just looking for ways to simplify things. It's like, rather than try to solve for everything, maybe first, we should try to solve something. Does this solve the proton puzzle mystery? I mean, why do these things take the parameters that they do? I don't know. Is it because, oh God, hold on. Ah, is it because they seem to need to be equivalent to hbar? I've gone through too many things. It should, these things, okay. I'm just saying that when Planck did that derivation, how do we solve the black body catastrophe? Legend has it that in a moment of desperation, he literally did a kludge. He's like, what would I need to put in here for this to work? Something like nanometer wavelength or something that ultimately ended up being coming out to be about like 6.6 or something joule seconds, or energy per second. That was Planck's constant, and then you could often simplify it by dividing it by 2 pi. You get your elementary unit of action, and well, if all these different things have all these numbers where it's like, all right, spin half, it spin one, spin this, spin that. It's like, okay, that's fantastic. What is spin? Something that there's a lot of hand waving about. That's why very often it's just listed as angular momentum, because if you just do this, what is h bar? Units of, let's get more. Angular momentum, action, elementary viscosity, total angular momentum, elementary action, kind twisted 3 form, a lambda h, thermal time. I don't know what that stuff means. It's like, all right, an action. Okay? You multiply energy by seconds. Well, F equals ma. The energy is just force times distance. It's like, all right, I got a bin on a washing machine. I give it a little tap. I give it some force. Now, that force, if I go over a distance, I can do 1 full revolution. There we go. We got some energy there. Now, if I want that energy to continue, I'm going to have to divide that by a certain amount of time. So then we have power, because then you have energy divided by your time. That's going to be your power. Now, as long as you have that power, we're going to be able to continue going on. So it's like, I unplug my laptop, only going to have so much power, and or when they shut me off. So, but that's the thoughts there. Let me see. Oh God, let me actually pay attention. Can you smell what the proton is cooking? The terrible thing is that's probably the easiest way to communicate some of these ideas. That's why I did things like the spherical God cow. Why? Well, you're just playing on the concept of the whole God particle that annoys physicists, and literally the spherical cow, just meme of, yeah, there ain't no spherical cow. You combine them, it's like, well, that's cool. That's a ginormous number. You divide it into the energy density, and it looks a lot like a dimensionless cosmological constant, which I start to think, I'm like, again, I ain't a professional. I'm just like, if you just take the square root of the cosmological constant, you get the basically the radius of the observable universe. That occasionally makes me think, is this just an observational effect? I don't know, because if there are certain observational effects, if we can account for them, maybe we can better figure out what is going on. There's commenting, why do they say pi r square? Pi r round, cornbread r square. I'll show myself out. Nyuk, 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 nyuk. The cornbread constant. God. Pi the sailor. Pi the sailor man. Dun, 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 dun. Oh God. Oh God. The jokes. The jokes. Um, honestly, I say I spent a day with Thad and Echelon about a year or two ago. They're like, let's figure out what's going on with quarks and stuff. It was a fantastic exercise. We didn't make any progress. We didn't make any progress. Really, really, it's like we tried real quick. We couldn't. We were using Thad's interpretation, and we were trying to see if we could figure out something. We didn't find anything better than what we have in the standard model. That's the thing. It's like whatever we do, it's like we got to make sure that unless you're going to redo everything and then be able to quantify and replicate all the stuff we have with the standard model with less stuff and be able to explain more, fantastic. I think of that problem you might actually solve like the Yang-Mills mass gap problem, because at least when I read it, it kind of sounds like Professor Wooden's asking you to basically write an entire quantum field theory. I know they're trying to explain the mass gap, but it literally says, and then a consistent theory. So if you can just, that's why a lot of people just, I think, just try to modify the standard theory or do these little things. I'm like, let me just look at other interesting relationships that maybe we could use as intuition that maybe fill in the gap. So the standard model goes from that picture that Professor Keating shows as, okay, it's a little off center there, to it's like, can we get it to just bounce? Can we get it to balance on 4 even legs? Do we need 4 even legs? Do we need 5? Do we need multiple? Do we need 26 legs? I don't know. But again, I'm just looking for, as Bill had stated, Occam's razor. Just, can we do something more simple with less? And then attempt to interpret it, but also you got to be careful, because it's like, you find something cool, it's like, well, let me try to explain everything. So you just got to be careful. Now, if certain things naturally fall out, because I'm like, at first I was trying like random numbers. I'm like, oh, this is about this, is about this. I'm like, let me just look at them directly. If it's kind of a match, maybe there's something there. If you're using things with like 9 significant digits and it seems to match for 8 because there's a little bit of rounding there, maybe there's something interesting there. And it's like, again, to do the whole, let's do a divide by pi thing. I don't think you could do it with this. Just because this, you're gonna have to go, okay, well maybe you could. But then again, it's like, well, what's your confidence gonna be? And then again, I also need to admit that I'm like, if the Compton radius is derived through that, it's like, well, I'm deriving this through setting it to hbar. So of course, maybe we would expect that difference of 2 pi to be there, because we can go back over here. And then we got this. Okay, so we got our 2 pi. So I'm assuming that this 2 pi literally comes from if you did full Planck's constant rather than just the hbar. Okay, one last thing. I'm sorry, I'm bloviating. Why might there be like that 4, that 2 there, aside from those Planck's constants? So, quantum speed limit. Why the heck am I showing any of this? All right, let's take a quick look. Okay, go down to the bottom. Full disclosure, I was doing this because this is basically the thing I was actually able to compute. So long story short is, this apparently is the speed limit of quantum information of actual matter. So basically it's 2 divided by hbar pi equals about 6 times 10 to the 33 inverse seconds energy. Joule seconds, it's just the inverse of this dimensions. It's inverse action, or inverse spin, or whatever, however you want to quantify it. Okay, the process, this establishes a strict upper limit on the number of calculations that can be performed by physical matter. the processing rate of all forms of computation cannot be higher than this number. This 6 times 10 to the 33 operations per second per joule of energy. This is including classical computers, since even classical computers are still made of matter that follows quantum mechanics. Okay, and they go on about how important it is. So I just look at this. I'm like, 2 divided by hbar. I'm like, when I write this out, I prefer doing it 4 just divided by Planck's constant. Because if it's 4, we're just 2 times 2. And then times 2 is just, that goes to 2 pi. So that equals Planck's constant. So I just enjoy doing that, because if you do, hold on, well, 2 divided by hbar pi, blah, 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 it gives you this number. Basically, yeah, inverse angular momentum, or you could rewrite it as just 4. You can either do 2 pi that, or it's Planck's constant. Actually, you know what, just for argument's sake, I think this is how we just kind of reduced it. It was just 2 pi hbar. Okay, there we go. So it gives us the same number. Now we have 4. Is this why there's 4? Is this why this seems to be the case? Why we have that 4 alpha thingy? Because it's literally just 4 divided by that circle thing, and then, okay, so where are we trying to get to? So this gives us proton radius. This gives us the Compton radius of the proton, because that's what it is, which is this range of the strong force. Okay. So that's something Bill might find that useful. Just because if you're looking at things that I was looking at, I looked at that like a year or so ago for completely different reasons to try to, yeah, I go down a lot of Wolfram holes. And again, a lot of them just come around in a circle. It's like, oh, well, somebody already did that. Hey, at least I know it now, or at least I performed the computation and can look at someone and be like, okay, this seems familiar to that. So, all right. So, all right. Well, Dave, we're going to wrap up right now anyway. Say, hey, thank you all for watching. Take care of yourselves. It's a wacky and wild world out there, and let's hoping for a better tomorrow. Catch you all on the flip side. Peace out, everybody.